So now that we've developed some theory around the use of logarithms, we can use that theory to help us prove something that in the past we have only proved partially. So in other words, the power rule says that the derivative of x to the power of n is equal to n times x to the n minus 1 for any real number n. So the missing link here is that in the past we've only been able to prove it for rational numbers n, but now we're going to be able to prove it for any real number n. And it'll be a very simple proof following the strategy that we mapped out earlier with the logarithmic differentiation. So to prove it, let's just start by letting y equal to x to the n. We'll apply ln to both sides of the equation. I can now take the n out and differentiate each side. On the left-hand side, I got 1 over y times y prime. Now n is a constant multiplied by ln of x. So that'll be n over x, or n times 1 over x. And then I'll multiply the y to the other side. So we have y over x. And then putting the original y back in, which was x to the n. And then simplifying x to the n divided by x, which will be x to the n minus 1. And there we have it. We've proved the power rule. And in this case, we were able to assume that n was any real number. There was nothing that we did here that made us need to assume that n was anything other than just some generic real number. Now I just want to take a moment to sort of compare the difference between some of these functions that we've encountered. So for instance, we've encountered exponential, power functions, what I'm going to call super exponential I'll explain in a moment. But the derivative of f of x to the power of n we know is going to be like a power function, where I'm using the power rule here. Because we've got a constant in the power. So we know it'll be n f of x to the n minus 1. And whatever f of x is, we can multiply by the derivative. Right? So there we're applying the chain rule. So that one we had to use the power rule. Suppose now I have something of the form b to the power of g of x, where now I have some function of x in the power. So this is actually going to be an exponential function, so we're going to use the exponential rule. So we've got b to the power of g of x. Well, we know this is going to be b to the power of g of x times ln of b. And then because g of x here is in the power, we'll multiply by the derivative of g because of the chain rule. So you see there's a distinct difference there between a power function and an exponential function. Right? So for instance here, let's think of a more concrete example. If I've got, for this one we can think of an example where maybe I have x squared minus x to the power of 5. Of course, we just have a constant in the power, so it'll be 5 x squared minus x to the power of 4 times the derivative of x squared minus x, so 2x minus 1. Now suppose I have something like this, where it looks more like this, where I've got a constant in the base, and then some function in the power, like let's do with x squared minus x again in the power here. Okay, well, we know it's now an exponential function, so it'll be 2 times x squared minus x, ln of 2, and then again times the derivative of x squared minus x, so 2x minus 1. Now let's look at something that's different from both of these, where we've got now a power in the a base of the exponent that is a function of x, and then a power that's also a function of x. So we've got a variable expression in the base and a variable expression in the power. So this is what I'll call a super exponential. So this one we don't really have a rule for, but we can use logarithmic differentiation in this case. Where we know that, for instance, if I take ln of both sides, I can then use the properties of logs that lets me bring that power out. And now I can solve for y, or solve for y prime implicitly. So I got 1 over y prime equals, now I have to do the product rule here. So g prime of x times ln of f of x plus g of x times the derivative of ln of f of x, which will be f prime of x over f of x. And then I can isolate y prime. Okay, so it's a little bit more complicated, but yeah, notice just applying this logarithmic differentiation technique allows us to solve this case when we have a super exponential function. Let's practice this idea with a function of the form x to the square root of x power. So now you see we've got a variable expression in the base and a variable expression in the power. So we'll start by applying natural log to both sides of the equation. I can then bring the power out. So I've got the square root of x times ln of x. Now I'll do 1 over y times y prime. So I'm taking the derivative of the left side, and then we'll do the product rule on the right side. So the derivative of the square root of x will be 1 over 2 radical x times ln x plus the square root of x times the derivative of ln x, 1 over x. And then I'll multiply y to the other side. So here we'll have ln of x over 2 radical x plus, let's see, square root of x over x simplifies to 1 over the square root of x. And then the final step would be putting my original y back in. So x to the square root of x times ln of x over 2 radical x plus 1 over the square root of x. Okay, so anytime I have this form, right, where it's in the form f of x to the power of g of x, we can do it this way, using logarithmic differentiation. An alternate way, so you guys can perhaps try this out on your own if you want. You can express f of x to the power of g of x as e to the ln of f of x to the g of x, so that would be multiplied by g of x. And you can work it out this way. Here I would be careful doing it this way, but you should get the same result if you do it this way. So in this case, if I have this x to the square root of x power, I can write this as e to the ln of x times the square root of x. Notice that gives you the same expression here that you're differentiating. Anyway, you can try that out on your own to see if you get the same result. Now, the last thing here we want to look at in this section is expressing the number e as a limit. So we've defined e before in a somewhat weird way. We said it was the number whose limit was equal to 1, but here let me think of this in a different way. So let's start with what we know about ln of x. We know that f prime of x would be 1 over x, and in particular f prime of 1 is equal to 1 over 1, so it's 1. On the other hand, I can write f prime of 1 in another way as a limit. As h approaches 0, f of 1 plus h minus f of 1 over h. So this would be the limit. As h approaches 0, f of 1 plus h would be ln of 1 plus h minus ln of 1 over h. And then we know that ln of 1 is 0. So I'm left with 1 over h ln of 1 plus h. Since we're multiplying 1 over h here, I can bring it in to the logarithm as a power, using a property of logarithms there. So we got limit as h approaches 0 of ln of 1 plus h to the 1 over h power. Okay. And we know that f prime of 1 can be expressed as this limit, where we actually already know that this limit has to equal to 1. So if I raise both of these sides as a power of e, well, we know that e to the limit of ln of 1 plus h to the 1 over h power, we know e raised to the ln power just are opposite operations. So this would be the same as the limit as h approaches 0. E to the ln would just cancel, so we're just left with 1 plus h to the power of 1 over h. So here we have one way of expressing the limit as h approaches 0 of 1 plus h to the power of 1 over h is equal to e. So we've expressed e as this limit. Or here we can write it in this form. Right, so we know that the limit as x approaches 0 of 1 plus x to the power of 1 over x is equal to e. And that would actually be equivalent to writing it in this form here, because here we can just do a simple substitution. So if I set x equal to, say, 1 over t, then of course as x approaches 0, 1 over t goes to infinity. in this case from the right. And our limit then transforms into this. The limit as x goes to infinity of 1 plus 1 over x to the power of x. It's just another way of getting e.